Hello, my name is Matthew Landis, and this is my Lab 3 presentation. This lab is our first real-world application of magnetic fields. Real-world observations as well as digital analysis is done, applying many physics principles previously discussed in class. Our primary goal of the lab is to observe and later model the impact that permanent magnetic dipoles, like our small cylindrical magnets, have on a magnetic sensor. On the top left, you can see the simplified bar magnetic formula, which is used frequently in this lab. On the bottom left, you can see the more complicated entire formula, which is used when we're operating at the 45-degree angles. In the middle, you can see the formula that allowed us to do some modeling, which will be explored further in the lab report. And then to the right, you can see two of the formulas needed to solve for values used later on. The experimental data was collected by taking the standard magnet for this class and using a ruler as well as our phone's magnetic sensor. Before we can make any calculations, I went and used the procedure outlined in the lab instructions to locate the sensor in the phone and align the phone with the Earth's magnetic field, part of which entailed making the X component of the measured field as close to zero as possible. On the top left, you can see that process, as well as on the top right, you can see the magnet being used. After distance measurements were taken, using for the magnetic field in the X that were being measured to the desired value, ranging from 70 to 220 microtesla. After doing similar measurements for the magnetic field positioned 45 degrees off axis, we had all the data necessary to complete our computational model. To solve for the n value in the formula, b equals k times r to the power of n, we can take the log of b and r to create a plot where the slope of our line of best fit is the value n. This allows us to use this value to simplify many of the calculations that were used later on in the lab. On screen now is some of the code that I used to model the interaction from the lab. These have been updated from the starter code to generate the magnetic field which is observed at different locations. I solved up for all these values at the 6 coordinate directions around the magnet, all of the distance d from the magnet. Afterwards, I took the vectors for each v, created arrows to simulate their position, direction, and magnitude. This allows us to begin comparing with our experimental data. Next, I took the d perpendicular value from the experiment, which is the distance away from the phone that creates a 100 microtesla x component, then slid the phone up by this amount as well, creating a 45-degree angle with the magnet and my coordinate axes. This required us to use a more complicated magnetic field formula, which takes into account the direction as well as the magnitude of the field. I've provided a link on screen now and as part of my submission as a comment. As you can see in the print screen of my model, I modeled the magnet with its approximate size and magnetic dipole. I then calculated and represented the magnetic fields at the positions discussed in my code. The 2 orange arrows on screen represent the field directly on axis to the magnet, while the 4 cyan arrows represent the perpendicular positions off axis. The small purple arrow positioned in the upper right corner represents the magnetic field at the position 45 degrees off axis in the x and y. In order to make this model, I had to make some assumptions. That for the 6 positions, the one directly with the magnets were directly in line with the magnet in some way. That way, I was able to use the simplified calculation. Additionally, this model assumes that there are no other magnetic fields that influence at the observation position. This final assumption is what I believe caused the greatest difference between the calculated field and the observed field. When doing the calculations, we made sure that the field on the X was 0. However, other fields, such as the ones induced by our smartwatches or even phones itself, likely had an influence on the data. The model was able to generate very similar data when calculated entirely on the x-axis in simplified form. However, at 45 degrees, the model generated a field with no z-axis, which did not match my experimental data. However, I believe this is the result of experimental error, such as the magnet being positioned in 3 dimensions. On screen now, you can see the data. On the x component nearly matches up between the experiment and the model. However, there's a great difference in the y and z components. If I had not begun each experiment by zeroing out the x component and aligning the phone with the Earth's magnetic north, the Earth's magnetic field, natural field, would have contributed in the x component, which is what was being used to calculate for the n value. Additionally, the final part of the experiment required us to consider the y component as well, which is why we had to isolate the Earth's field. To compensate for this, we first calculated the Earth's field on the y by measuring the magnetic field present, and then subtracted this from the observed vector. If I had simply stuck 2 magnets end to end and ran the experiment again, the measurement would have observed a greater magnetic field. This is because each of them, if stuck in line, would generate a field in the same direction. The field would not have doubled, however, because even if the magnets were identical, the second magnet would be slightly further away from the observation location. Thanks.